record on this computer. Okay, so good afternoon. So today we are going to learn how to perform a completely randomized block design ANOVA F test in SPSS. That includes an assumption check. And then we are going to learn how to perform the multiple comparison that would follow the CRBD F test in SPSS. And both of these techniques would be things that we're going to utilize on assignment 3 of the lab material. Okay, so the data set that we're going to use for today's lab is the languagetest.sav data. So this is available on the course website. So I'm going to load that into SPSS now. Okay. Let's see back here. Open. So we have this languagetest.sav. Yes. Okay, so you can see that the structure of this data is a bit different from the type of data that we would have worked with before, in that it has one explanatory variable, and then it also has one what we're going to consider a confounding variable. So the purpose of our completely randomized block design is to test for a mean difference across the levels of the explanatory factor while controlling for the levels, or while controlling for this confounding or block variable. So when we look at the data closely, you can see we have subject, we have test, and we have score. The question states, at the 5% significance level, did the data provide evidence that the mean scores from the WUMV, the WSA, and the WAIS language tests differ? So it's a pretty standard type of ANOVA question. So we just want to know, is there evidence of a difference across the levels of the test in terms of the average score achieved on the test? Now, in this situation, we are also considering the fact that for each type of test, we have the same person that wrote that test. Okay, so the rationale here would be, say that person 1 has a more natural aptitude than person 3. Well, you might consider that person's aptitude to be a confounding variable. So if person 1's aptitude is higher than person 3's, you would expect their average score to be higher than that of person 3's. But we don't want our ANOVA F test to take that aptitude into consideration. We are trying to make a comparison across the levels of the explanatory variable, which is the test, while accounting for this aptitude in each person, but we don't want that person's aptitude to play into our F test. So this is the type of data that we would use a completely randomized block design for. So again, as a reminder, the completely randomized block design is essentially an ANOVA F test where you would compare the mean response at the levels of some explanatory variables while accounting for a confounding variable that's present within the design. So we want to compare the test results, or the average scores for the test types, while controlling for, let's say, the aptitudes of the person writing the test. Okay, so we're going to do a CRBD in SPSS. The assumptions of the CBRD are as follows. So we have randomly selected blocks. We have independent samples. We have normally distributed populations. And we have constant variance. Okay, so the randomly selected block assumption and the independent sample assumption, those both come from experimental design. So as we've determined in the past, when we want to check the first two assumptions of an ANOVA procedure or even our t-test, we really just have to know where the data came from. So in this particular illustration, it is said in the lab manual that the variables in this data set doesn't seem to give any strong indication. Just for the purposes of illustrations, let's assume that these are true, so just so that we can carry on with the test, because really performing the test in SPSS is what we're interested in. So assume the blocks were randomly selected and assume independent samples in each population, i.e. that we collected simple random samples. Okay, now to verify the normality assumption, we can do a residual analysis. And we talked about this idea in the previous class when we looked at residual analyses for the one-way ANOVA. So that's going to work in the same way here. Basically, we're just going to create a QQ plot of the standardized residuals. So to do that, we're going to go analyze general linear model univariate, same setup as before. And then we will click, we will put the score as the dependent variable. And in the fix factor, we're going to enter both the subject and the test. So the residual computation for a CRBD is different than the residual computation for the one-way ANOVA because we're accounting for both the subject and the test factor at the same time. Then we're going to click save, and we're going to do standardized residuals, unstandardized predicted values. So again, same idea as what we had when we checked for normality in the ANOVA experiment. Okay, we click continue, and then we click OK. So you can see that now we have our values generated in the table here. Oh, sorry, what's gone wrong? Okay, let's see if analyze descriptive QQ plots. Is this actually gonna work? Yeah, wait, this is weird. Okay, so general linear model, univariate, fix factor, subject and test, dependent variable score, save, standardized residuals, unstandardized predicted values. Okay. All right, so I think the issue here is that the test name is a variable type. So I think what we have to do is restructure this. So let's just try that. So what we're going to do is we're going to transform the testing variable into a coded integer. So we're going to go data, and then we're going to go, is it restructure or? Sorry, one sec. I just need to check how to do this real quick. It's a recode. Should be a recode option somewhere. Recode into different variables. Okay, so let's try recode, test, old new values. Okay, so WAIS is going to go to 1. B is going to go to 2. And WSA is going to go to 3. Continue. Okay. All right. Analyze, general linear model, univariate. It's very strange. All right. Let's just back this part up. Try this one more way. Data, recode into different variable, test, old new value. Okay, so WAIS goes to 1, WUMV goes to 2, WSA goes to 3. Continue. Oh, output variable name, test, recode. Okay, and then analyze, general linear model, univariate, score, subject, test recode, save, unstandardized, standardized, continue, click OK. There we go. No, it still didn't work. Oh, all right. I have to pause this for a second. Resume. All right. Okay, we're back. Sorry, so there's going to be a little bit of a time segment in the video that is useless material, and you can just watch me stumble through SPSS, but I realized what I did wrong. So, okay, we're working through the completely randomized block design here. We want to test for a difference across the levels of these 3 variables. We want to account for the person as the block variable. So to do this, we actually have to set up the entire experiment at the same time. Otherwise, we can't produce the QQ plots. Okay, so to set up a CRBD in SPSS, we go analyze, general linear model, and then we click univariate. So here and here, we're going to move our dependent variable, which is score, into the dependent variable column, and then we're going to move subject and test into the fixed factor column. Okay, now what we have to do is we have to basically tell SPSS what subject and test are. So these are considered main effects in the SPS system. So we click on model, and you'll see here, it'll say full factorial, build terms, build custom terms. We click build terms. Okay, so we went analyze, general linear model, univariate, and then we dragged score in the dependent variable column, and we dragged the other 2 variables into fixed factor. Under specify model, we click build terms, and then we drag, and then under type here, we click main effects. So right now you probably have it set at interaction. We click main, and then we drag subject and test into the model box. All right, and then we click continue. Okay, then we go, so we're gonna output the CRBD ANOVA table and we're going to output the residual plots or the residual values at the same time. So after we've clicked everything in model, we click save. We click standardized residuals, unstandardized predicted values, and click continue. And then we click OK. All right. So in the output, this is the ANOVA table for our analysis. So we actually have the CRBD ANOVA table given to us up front. So we can just take this now because we're going to use it later anyways. Okay, and then we'll insert that into our output. Now, we want to check the normality assumption. Oh, sorry. So we want to check the normality assumption. So the next thing we're going to do is build a QQ plot of the residual values that were generated when we went through that process. So we're going to click graphs, analyze, descriptives, QQ plots. We're going to take our standardized residual values. The test distribution is normal, and we click OK. And then here's our QQ plot for the experiment. So we're going to take this with us into our SPSS output. Okay, so here we're going to insert our QQ plot. Okay, so we can see here that we have a little bit of a couple of points that are deviating in each tail, but for the most part, the observations fall quite close to that line. Right, so I think we're safe to say the normal probability plot of the standardized residuals gives no evidence to suggest that the variable of interest is not normally distributed. Okay. And the next thing we want to do is check the constant variance assumption. Now, there's a number of different ways that we can do this, but a nice, like, sort of compact way of doing this is building a scatter plot between the residual values and the predicted values. So in SPSS, we're going to go graphs, legacy dialogues, scatter/dot. Okay, we're going to click simple scatter. On the y-axis, we'll put our standardized residual values, and on the x-axis, we'll put our predicted values. Okay, then we can label this, so standardized residuals versus predicted values. Continue. Okay. Okay, and then here is our plot, our outputted plot. Now what we are looking for here is lack of trend. So what we want to see in this plot is basically just a random cloud-like shape, which is actually what the data is showing us. So if we insert this below, picture from file, the last screenshot. Okay. So we can see that when we studied this plot, the standardized residual versus fitted value plot does not show any evidence of a relationship between, or it does not show any evidence of a relationship. Period. Okay, that is, the points appear to be randomly scattered, sort of like a cloud. Okay, so that's what we would want to see. Therefore, the plot gives no evidence to suggest that the constant variance assumption, or that the variances of each treatment group are not the same. So this is actually what we want to see when we create this kind of plot. So this is kind of like a nice shorthand way of checking the constant variance assumption. So we've just done a predicted value plot versus a standardized residual plot, and we're looking for a cloud-like shape. So we don't see any kind of trend, which is the big thing. You don't see a linear trend, either positive or negative. You don't see any curvature in either direction. The points just look randomly scattered. Okay, so this shows that we have constant variance. So now we can actually move on to our hypothesis test. So in the hypothesis test, we are testing for evidence of a treatment effect. So since it's a CRBD, we're going to have alpha 1 equals alpha 2 equals alpha 3 versus H subscript A. There is no treatment effect. And that's the same thing as saying all treatment means are different. Okay, so we're going to test at the 5% significance level. And then from our previous work in SPSS, we already have our ANOVA table. So we can insert that here. All right. And then the value that we are using from the ANOVA table would be the F value for the corrected model in this case, or sorry, it would be the F value for test. So you can see that we have corrected model, intercept, subject, test. So we want the F value for test, which is shown here. So that's the F value for the treatment effect because we're looking for a difference across the levels of the test. All right, so here we're going to have F equals 31.798. Okay, on step 4, we can see our p-values are unchanged. So then on step 5, we can reject H0 since our p-value is clearly less than alpha. And then on step 6, we can say at the 5% significance level, the data provide sufficient evidence to suggest that there is a difference in mean response in the mean score on the tests. In the mean score achieved on each test between at least 2 of the mean scores achieved across the different tests. Okay, got through it. Right, so you can see that the process is actually pretty much the same as it was with the one-way ANOVA. The only difference is that when we set the model up, we have to go through this analyze general linear model univariate selection. And then the mistake that I made originally is once we are setting up a CRBD, we go into the model box and we have to make sure we have build terms, main effects, and then the model types in here. So once we have that structure set up, we can output both the CRBD and the residual values directly. And then we can build the QQ plot and that scatter plot of the residuals versus the predicted values, and we can finish the test. Okay, now the last thing that we have to do is perform the post hoc tests. So if we go back to the question sheet, it says, should a multiple comparison of the treatment means be performed? Okay, well, in this case, we rejected the null hypothesis. So we can say, since there is evidence of a difference between the mean scores of the 3 tests, we should perform a multiple comparison of the treatment means. Okay, so to perform the multiple comparison, we will go univariate, just like before actually, we go analyze, general linear model univariate. That's gonna open up this table here. And then we click post hoc. So this would pretty much be done in the same way as it was for the one-way ANOVA. Okay, now we're interested in a post hoc about the test, not about the subject. So we move test over to post hoc. We select the type of post hoc procedure we would like to perform, which is the Bonferroni. And we can state All such things appear to be done. So then we click continue. Okay, it's going to output a lot of the same value. All right, and here's our multiple comparison table. So we can take this with us, move it over here. Okay, insert pictures from file. Okay, so just like before, we are going to have in this multiple comparison, we have 3 choose 2 equals 3 comparisons of interest. All right, so the first comparison will be WAS versus WSA. Okay, so the WAS versus WSA gives a p-value of 0. We can also see that the 95% CI doesn't include 0. So for this test, we can say since p-value equals 0.000 and or because CI 2.5878 to 5.0789 does not include 0, there is significant evidence of a difference between the mean test scores for the WAIS and WSA tests. Okay, the second comparison will be WAIS versus WUMV. So since p-value is again equal to, oh, it's not 0.00 here, it's 0.02. Okay, or because CI, which is 0.6711 to 3.1622, does not include 0, there is significant evidence of a difference between the mean test scores for the WAIS and WUMV tests. And then the third comparison would be WSA versus WUMV. So since p-value for this test is also 0.002, wait, what? How is that possible? It's very bizarre that all these numbers have worked out this way. Huh. Okay. Okay, so since p-value here equals 0.002, or because CI, which in this case is just the opposite of the one before, it's very strange that it worked out like that, not include 0, there is significant evidence of a difference between the mean test scores for the WSA and the tests. Okay, so then we can say at the 5% significance level, the data provide sufficient evidence to suggest that the mean test scores differ between the WAIS and WSA tests, the WAIS and WUMV tests, and the where's my third one? There it is. WSA and WUMV tests. There we go. All right, so that's a complete randomized block design testing procedure in SPSS. It's for a fairly simple illustration. So again, basically the same process as with an ANOVA. So we do an assumption check, we perform our test, and then we can do a multiple comparison if we reject the null hypothesis in the ANOVA test. The mistake that I made earlier was I didn't properly set the model up in SPSS beforehand. So we have to make sure that before we run our test or even do the residual analysis, inside the analysis general linear model univariate, we click model, we have build terms, main effects, and we drag the two covariates into the model and then click continue. And actually, you don't have to do this right away, but if you wanted to, you could already set the post hoc test up right away. And that way, if there is difference, or if there is evidence of a difference from the ANOVA table, you already have the post hoc test output and you don't have to go through and recompute it after. But the most important part is that we get this part set up before we do any of the other analysis. Because if you don't do that, like what happened to me, you won't get residuals printed out. And then you'll start going through the process of trying to recode things, and it's a bit of a mess. Okay, so that's all I wanted to show today, was just the process of doing the CRBD and SPSS. As usual, if you guys have any other questions, I'll be around to answer them. And if not, have a good weekend and a good reading week. And I guess I will talk to you guys in 2 weeks, not next Friday.